So welcome back, everybody, and welcome to this week's topics. So what we are going to do today is to continue a little bit this kind of review of neural networks. So which in a way is very much top-down, because many of you have already studied neural networks, you've written your own code. But the coding which you will see here can serve as an inspiration if you want to move on. And it can also serve as a way just to refresh what you have done. Then we are going to move into the next topic, which is the topic of convolutional neural networks. And that fits the project of many of you. So many of you actually want to do something which has to do with images. You would like to use CNNs as a first step. And it's pretty common if you now think of the projects. So many of you have opted for doing just one project. So that gives you more time and the possibility to think over things. And it means that if you're looking at, let's say, images, one path is to look at image recognition with generative methods, which will be the final stage. But then you would typically start with CNNs, convolutional neural networks, which is a kind of state-of-the-art method for imaging. And then you would move on to, let's say, autoencoders, which is another very popular method. So then we would cover in the project at least 2 to 3 central methods for, let's say, imaging. Now, for those of you dealing with, let's say, differential equations, starting with a neural network, which is a building block, would be an essential first step in, let's say, solving differential equations. And then you can add to these autoencoders, and you can move on to physics-informed neural networks, just as an example. Or if you're dealing with other types of problems, you can look at generative methods, etc., etc. So this is a kind of path which you can follow, where you actually use different methods. And CNNs is a very important entry to many of the applications which many of you will encounter in your thesis work, in your research, and so on. Yeah? Hey, could you say it again? Most likely not, actually. So what we will do in the first part, which is roughly till the middle of March, is CNNs, RNNs, the physics of that, no, the mathematics of that, and autoencoders, principal component analysis, which is linked also with autoencoders. And we will say something about graph neural networks. And then we switch to generative methods. So that's what I will cover in the lectures. Also because these are the things which I do research with, right? But then, as you probably have seen, there's a lot of flexibility here, which means that in the projects, you should feel free to explore things which you find relevant and interesting. But this is also a little bit in the spirit with the course, which has a self-study element as well. So we want to keep that, but at the same time, there are specific topics which we go through during the lectures, which hopefully may be of interest to a broader audience. Okay? So the problem with when you do machine learning and AI methods is that there is so much going on that it's actually very difficult to cover everything. And you will see that the university has dedicated courses on specific methods. And in that case, it could be perhaps relevant to follow one of these more dedicated courses. And the applications here have been much more towards the natural sciences. One thing which I wanted you to take a look at are examples of projects from last year. And that can serve as a kind of inspiration. And I see that from the input I've gotten from you that most of you would like to do a longer project. So feel free to do that. The only constraint we have then is that we would like to have a one-page feedback from you guys, a kind of mini report in the middle of March, where you just simply state what you have done, where you are, and what kind of problems you foresee, etc., etc. after the lecture today, we will have a presentation of some of the projects. And some of the people who will make the presentation, they're also interested in partners. So if somebody would like to team up, I mean, feel free to discuss with people. We already have many people who have decided what to do and have already formed groups. So there is a lot of activity going on physics-informed neural networks with different types of differential equations. Okay, so besides this, I just wanted to quickly remind you of some of these specific textbooks which you can find online. So, yeah. Yeah.
Is there an overview anywhere, or can you give us some information on what would be the concrete requirement differences? Because obviously I expect that you can do one project that is the size of someone else's one of two projects.
Yeah, so we haven't made, how to say, clear distinctions between that. But often what you would see is that the long project often incorporates what you would find natural with two projects. So suppose you're doing image analysis, just to give you an example. Then it would be natural if you want to write two projects, to have a first part where you do CNNs and autoencoders and explore these methods, just to give you an example. And last year we had people who actually looked at the MNIST data set, and then they went on with generative methods like Boltzmann machines and variational autoencoders and explored them in the second project. But you see also it's not so difficult then to merge this into one project, because then you just write one introduction, and instead of rewriting the same thing in the second project, then it's natural then to make this into one project, because you're dealing with the same data set, but you are studying different methods. But we've had people who wanted to do totally different things. So we had a group last year which did CNNs and autoencoders on images, but then they applied generative methods in the second project for a totally different data set. Then it's natural to split it in two. But suppose now that you have a data set you want to study with different methods, then it's pretty natural to actually write one project. But you should cover at least some of the discriminative methods we discussed now, just as this example with the convolution neural networks and autoencoders. People who study differential equations with time series or time-dependent differential equations, they did RNNs and autoencoders in the first project, and then they went to pins in the second project. That could be easily two distinct projects. I hope that was a kind of answer. So it depends very much on you, because many of you have a specific problem you want to study with different methods. Then it's common to just have, it's reasonable to just have one long project. I hope it's a little bit clearer, because we want you to have this flexibility, but clearly many of you are perhaps not used to have all this flexibility in a course. And you're much more used to answer this and this question. But we actually want you to go a little bit away from that kind of setting and allow you to explore things which are interesting to your research and the things you want to do. And then every year there's somebody who just wants to have fun and explore different methods. That's also fully allowed. Sometimes not having well-defined paths can always lead to some confusion. Yeah?
Sorry. Also the course with SNK 4155 is also project-driven?
Yeah, that's project-driven. Yeah.
It's also project-driven.
Yeah.
So there we can also have like one long project.
Right? No, that's a three different projects.
Three different projects.
Yes.
And are we also free to select the projects, or
no.
are they?
No, they are more set.
Okay, they are just set.
Except for the last one.
Right.
Yeah.
Right.
So the books which I normally use when I give some reading assignments, and in the beginning it can be a little bit overwhelming, but many of you have actually gone through these things before. And essentially, if you're looking at PyTorch and neural networks, it's these 3 chapters of Rashka's text. If you're not interested in PyTorch, I mean, you can skip chapter 12 and 13 and use TensorFlow or your own codes if you prefer that. And the chapter for CNNs is chapter 14. And you will see that in my lectures, I've also borrowed a lot from that textbook. So one thing I actually wanted to repeat very quickly, unless you have more questions. By the way, take a look at these examples which we have from previous years. So I'm just going to bring it up again so you can take a quick look at it. So if you go into the doc folder and you go to the project folder, you will find one which is called project examples. And you will see here the applications to recurrent neural networks. This is actually a group who last year wrote their own RNN code, but they applied it also to language models. So it's a kind of stepping stone towards large language models. So take a look at that one. That was an excellent project. We had another project here which dealt with the long short-term memory methods for time series analysis. We had one which focused on convolutional neural networks and writing a convolutional neural network code. And these are things which we will discuss a little bit more next week in detail when we go through. Today we are going to discuss a little bit more the mathematics of CNNs, and then we are going to go into writing your own CNN code and how you can do that, and also obviously how you would use TensorFlow and PyTorch in doing the same things. So again, one thing I wanted to state very clearly here, so that there is no misunderstanding, you don't need to write your own code for everything, because there are so many libraries and examples out there that it's more you understanding what goes in and you tailoring this to your interests. So some of you are more interested in the coding part, and some of you actually want to use these methods on your data. So whether you use PyTorch or TensorFlow or your own codes, this is something which you have to decide. And in some situations, there are also libraries which have been developed for specific types of problems. And clearly, you should use these libraries. As an example, it's not so that you write your own code for automatic differentiation. You simply use autodiff. Now, you will also see that in the lectures here, I will, to a large extent, use the Jupyter Notebook, mainly because I run codes together with the lecture notes, which you see here. So this is also the files, which is the one which I normally recommend looking at before you come to the lecture. So just to give you a quick reminder, when we talk about neural networks, we actually defining an architecture, and that is the model. Like when you are fitting a polynomial with linear regression, the polynomial is your model to a given degree. Now, the model is given by the architecture of the network. So as we discussed last time, we have an input layer, we have an output layer, and the output, which we call y tilde, which is produced by the architecture, the model, is then compared with what we normally call a target value y. So the target value is the data which you want to reproduce. And if you think of it now, this is a typical procedure for a discriminative method, which means that you have some data you want to reproduce. Now, if I use a neural network for solving differential equations, then a neural network can be seen as a generative method because you generate a solution to a differential equation. And then you can use this solution to generate new data points which were not included in the fit, as an example. So a neural network is not something which you can rigidly think of as a discriminative model. It's also a generative one. It depends a little bit on the task we are dealing with. So there's a given number of hidden layers and neurons, And these become parameters you play around with. The activation function is one of the big topics. It's common to have the same activation function for all the hidden layers, but have different ones for the output layer. So you will see in the codes that this is something you can easily add to many of these. And there is a whole hierarchy of methods. We are going to come back a little bit to that. And then we have the last layer, which is the output, which is then linked with an activation function tailored to the specific problem. And then you need to define a so-called loss function. And if you're dealing with, let's say, a linear regression type of problem, you want to fit some function, these are the parameters theta which you would be optimizing. And you would then optimize this function here by calculating the gradient. And that's your optimization problem. So for neural networks, as you know, I mean, these parameters given by the so-called weights and biases. And these are the parameters you then would have to update. The other topics which we deal with is the optimization part. And here, many people would typically start with a plain gradient method where you have a constant learning rate. That's a very common entry approximation to a neural network. And then you would replace that with better methods for updating this learning rate. So this is a very common procedure. You start with the simplest thing and you try to map out and see what you're getting. And then when you have that, you add improvements through adaptive methods for updating the learning rate. So that's a pretty common strategy. You often start with just one hidden layer and some few nodes, and you see what you get. And then you gradually increase and add more complexity, which means that when you run, just to remind you of neural networks, what you do actually is to see this as numerical experiments. And you would be running many of these experiments. And then at the end, you would settle down on the results which give the best reproduction of your data. So it's you at the end who decides what is a good approximation, what is a good model. And this can depend on many parameters, like how much time you have for doing this, when you have to hand in the report, etc., etc. So there's always there are always boundary conditions which influence your final result. And some of them are often not so easy to deal with, like how much time we have at our disposal before the deadline. Okay, so there are many ways also in the discussion. So I'm looking at neural networks from a more overarching point of view. And the problem is that you end up with many parameters. So which one should I tune first? Learning rate, or these typical hyperparameters which are included. So often you would tune the learning rate and the hyperparameters first. And then you will, after you find the reasonable results, you would then move over to, let's say, in the optimization part. After you tune the learning rates, you would then bring in adaptive gradient methods like AdaGrad, root mean square, or ADAM, and refine the results and see if you get improvements. But the typical parameter, which is normally tuned first, is something like the learning rate. You would set up a grid of values, and you would pick the one which gives you the best result. And with that one, you can then play around with further options like different optimization ways of updating the learning rate. And there are tools. You have grid searches, which you can bake in. Grid search with cross-validation is actually pretty common to use to find the right hyperparameters. You can use randomized searches. There's a tool, and actually there are more tools, which implements more complex algorithms to help you find a set of hyperparameters quickly. But often there's a lot of hand tuning before you settle down on the ideal network or the ideal number of parameters. So for many problems, you can start with just 1 or 2 hidden layers, and that works fine. You will typically see for this MNIST data set, which I'm using again and again in the lectures, that often you get a pretty good result with just 1 or at most 2 hidden layers. And the other question is actually which activation functions you should use. And you will see in the example codes that there are many examples of activation functions. So we have all this family with ReLU, rectified linear unit. We have the ELU, exponential linear unit. And then there is a whole family of these methods. And if you just search, so I can just give you one example here. So one type of function is actually called the JELU. I actually misspelled it here. So this is one of these functions which many of you will encounter and perhaps use. So this is called a Gaussian error linear units. And you can see in the figure here, there's a comparison between the exponential linear unit. And one of the reasons why people introduce these functions is that we can easily run into a problem in the training with exploding or vanishing gradients. So vanishing gradients is something you can easily see from this image here, because the input, depending on the value, if it's large, either negative, in this case negative, you will get an activation function which is flat, which means that when you take the derivative, the gradients can easily approach 0. So in the training of a network, so-called vanishing gradients will stop the training, and you may not have reached the optimal values of the parameters you want to train. So these are typical examples which people would play with as parameters in your architecture. So sometimes you can even see results in articles where people say that we know that this activation function shouldn't work well, but in our data set, it actually works better than the other ones. And we don't know why. Because you have so many parameters. Let me see here. We have a question from some people online. Yeah, there's a question here from online. How do they tune hyperparameters when the training takes a very long time, say several days, and LLM takes weeks and months for training? How do they find the best set? Now, one of the ways by which you would often do this is to have pre-trained networks. So that's the most common approach to it. And you will see, like in imaging, you have huge data sets to which you have pre-trained networks. So these networks would then have been trained on images of cats and dogs and so on. And then with a pre-trained network, you have hopefully a better set of parameters, which then can be used in a new training on your specific images of cats and dogs. So this is something which depends on from case to case. You would often start with a small model and then keep adding functionality to it. Like in my case, just to give you an example, I solved quantum mechanical problems, and we're also interested in quantum mechanical problems with pins. So then I solve a quantum mechanical problem with a neural network without time dependence. And that gives me a very good ansatz for the ground state of the system. And that gives me a trained network with parameters. Then I use that as an input in a pins code, a physics-informed neural network, where I'm also interested in the time evolution. But then I have a very good starting point. So that's often one of the strategies which people end up dealing with when you're looking after hyperparameter. I hope that was one type of answer. Now, one of the things which I just wanted to say a little bit about, because many of you will encounter the logistic function, and we discussed that partly last time, and that has been and still is a very popular activation function in neural networks. The reason for that is that this was meant as a very simple approach to simulate how a neuron sends a signal. So below a certain threshold, it just spits 0, and above a certain threshold, it sends out 1. And the sigmoid function was a very good way of simulating that. The problem with the sigmoid is that if it takes very large value, it gets very flat at the ends. And that led to the problem of vanishing gradients. And this almost stalled the whole field in the beginning of this millennium, because many of these networks were difficult to train. And there is a seminal paper by Xavier Glorot and Benjo, who found that the problem with a popular logistic function and their weight initialization technique that was at most popular at the time, namely random initialization using a normal distribution with a mean of 0 and a standard deviation of 0, actually. There should be a 0, which I've forgotten here. And they showed that this activation function and that initialization scheme had a variance of the outputs of each layer, which is much greater than the variance of its inputs. And going forward in the network, the variance keeps increasing after each layer until the activation function saturates at the top layers. And that's normally made worse by the fact that the logistic function has a mean of 0.5 and not 0. And the function actually behaves compared to, let's say, the hyperbolic tangent, which has a mean of 0, and that normally behaves better than the logistic function in deep networks. And the derivative of the logistic function, when you look at it, it could have derivatives which were close to 0. So in this paper, we actually recommend, if you have time, take a look at that paper, because that gives you some insights about the type of activation functions which are needed in the training of a neural network. So a typical calculation with a standard logistic function could easily lead to this problem of vanishing gradients. Another problem is that of exploding gradients, which we will encounter when we look at recurrent neural networks. And in the recurrent neural networks, we actually looking at products of different layers. And in case of the gradient becoming larger and larger, you are just accumulating products of gradients, and that can lead to exploding gradients. One of the tricks which is used, and that's a very ad hoc trick, is gradient clipping. That means that if it reaches a certain value, you just reset it to a smaller value, and then you keep iterating. So that is very ad hoc. So even if we talk about the mathematics of neural networks, there is a lot of, ad hoc procedures in order to prevent specific problems. But this is a field which is under evolution, and there is a lot of new insights from the mathematics of neural networks. Yeah, I'm gonna skip that a little bit. So the one of the functions which many of you have studied is this ReLU function, the rectified linear unit, and that suffer from a problem known as the dying ReLUs. And during training, some neurons effectively die, meaning they stop outputting anything other than 0. And in some cases, as you can see here, you may find that half of your network's neurons are dead, especially if you use a large learning rate. And during training, if neuron net weights get updated such that the weighted sum of the neurons input is negative, it will start outputting 0. And when this happens, the neuron is unlikely to come back to life since the gradient of the ReLU function is 0. And to solve that problem, many practitioners introduce this ELU function, which in a way avoids that. And then you have this GLU function, which also avoids that. So the question then is, what kind of insights do we get? So we often get insights from practicing. And what you see here is more something which follows from years of practicing with this different type of calculations. So you would see that this GLO function we mentioned, and also the ELO, often, but not always, performs better than the leaky ReLU, which is normally better than, so the leaky ReLU has actually, if you go back to this function here, the orange one is the ReLU. So the leaky ReLU has actually a slightly non-negative result. No, sorry, a slightly different from 0 result for non-negative arguments. That's what I meant to say. Sorry. And typically what people see is a kind of hierarchy where the ELU gives better results than the leaky ReLU, which is better than the ReLU function, which often then performs better than the logistic function. So when you present your stuff, this is a typical part of the experimentation you end up doing. And if you write it up as a scientific article, you would have to state this. We tested these and these activation functions so that people can actually reproduce your calculations. So the other thing I wanted to remind you of is typically that you run the calculations for all the hidden layers with the same activation function, because else you're going to go crazy with all the parameters. But the output layer, typical for classification problems, if you have more than just a binary problem, is to use the softmax function, which is pretty common. And for regression tasks, which means you fitting a function, you simply use the output from the network. So there is no modularization of your output through a function. So I'm going to skip some of these things here. You can just look at this and then take a, this actually in chapter 11 and 12 of the textbook of Benjo, Goodfellow, etc. There are actually lots of discussions about the optimization of a neural network. So I'm gonna leave out some of these things, but I wanted to say a little bit about the limitations of neural networks, because that brings you to a motivation of convolutional neural networks. So in principle, you need labeled data. If you do a supervised training, not when you're solving differential equations. Solving differential equations is an example of an unsupervised problem. So supervised means that you have all data labeled and you want to reproduce the data which you have. If you're solving a differential equation, you don't have a labeled data. So a neural network, even if many think of this as something dedicated to supervised training, can also be used for unsupervised learning. So solving a differential equation because you don't know the solution. You would just set up a set of points and you look after the solution of differential equation with a neural network. So in that case, it's an unsupervised type of problem. But many of these problems here, like imaging, are extremely data greedy. And a neural network is actually very much set up so that you deal with, at the end, with matrix and matrix vector multiplications, where the matrices and vectors are dense. So these are normally called affine transformations of your data. And what happens then is that this clearly limits what you can do. Because if you have a huge set of images, and each image is, let's say, 200 times 200 pixels, that means you would have 40,000 input nodes for every image, and you have 1 million of images, which is a typical case in these big data sets. Like ImageNet is a big data set which has been used to pre-train networks. Then clearly you have to think of different ways, and convolutional neural networks are a way to reduce the dimensionality of the problem. So at the end, many of the problems we're dealing with are multidimensional ones, and our task is actually to reduce the dimensionality of the problem and still do something meaningful. So the deep neural networks are often used on homogeneous data, and this is sometimes a limit. And for those of you familiar with, let's say, random forest or gradient boosted trees, there you can actually mix different data types. And many problems are actually not about predictions. So in natural science, we're often interested in learning something about the underlying distribution that generates data. And in that case, it's more difficult to cast these ideas in a supervised learning setting. Again, a differential equation, solving that one, if you think of a quantum mechanical problem, or you're solving a diffusion type of problem, then the solution to the problem can be interpreted as a probability distribution. So when I solve a quantum mechanical problem, I get the wave function and I square it. That is interpreted as a probability distribution. So I want you, the reason why I mention this is that many of you are going to deal with projects with pins. And these are problems which can be solved with neural networks at the core. And these are not supervised problems. These are actually problems, if you think of the diffusion equation, you're actually finding the probability of the system being in a specific state. So the solution to the diffusion equation can be interpreted as a probability distribution. So in that sense, what we see here, or what we say here, is that neural networks are much more flexible than it's often traditionally discussed in the literature. Especially when we move into the solution of differential equations, which many of us end up doing since we're doing natural science. So I wanted to give you a kind of a quick discussion of codes. And there is a set of code here which was developed by two guys who actually took this course the first time we had it. They wanted to write a CNN code, and they also developed a neural network code. So you will see that the codes here were developed by Eric Reber and Gregor Kaida. And the structure there is similar to what you will see when we discuss the CNN codes. If you want to build your own CNN code. If you're more interested in using this to specific data, then clearly I would recommend using libraries like TensorFlow or PyTorch. So let me quickly remind you of some of these things. So there are different classes here. And the first class deals with different types of ways to update the learning rate. So let me just quickly rerun this one. And in this case, you would have methods like the root mean square propagation. You have the method which is called ADAGRAD with momentum and without momentum. This is without momentum change. So I'm assuming that you've seen some of these methods. If not, these are things we can discuss a little bit during the lab sessions for those of you who haven't met them. Another possibility you have, in addition, you have momentum here, but it's also just to have a constant learning rate. And many people do that as a strategy in the beginning when they're setting up a neural network. They just have a constant learning rate and just run through with many different learning rates. And as I said, the big issue is actually that when we are dealing with an optimization problem, so let me quickly remind you of that. So we are going back to the whiteboard a little bit so that you have this clear. So when we are trying to find the optimal parameters, so as I said, at the heart of all of machine learning, there is an optimization part. So if we then look at the optimization part, if I now use Newton's-Raphson's method, which is based on a Taylor expansion around the optimal value. So I have a set of parameters theta, and I would solve this iteratively till I reach the optimal value, which is the case where the gradient of the cost function is 0, ideally. This one is now given in terms of the parameters theta. So these are both the biases and the weights of a network. These are the parameters. And you can have millions of these parameters. This is then given formally by the second derivative of the function, the cost function. So we would then have the second derivative. And I'm writing this as C of theta of n. This is a matrix. And this is we need to calculate the inverse. And this is normally called the Hessian matrix. And it's evaluated for the parameter at iteration n. And this is again multiplied with the gradient of the cost function, evaluated at the value theta n. So if you have few parameters, suppose you have 10 parameters. This is normally a 10 by 10 matrix. You are then going to have an equation here, which involves 10 parameters. So you can now think of having 10 lines down here. And if you do 100 iterations, it means that you have 10 times 100, 1,000 evaluations of this quantity here. So if you have 10 parameters, this matrix is a 10 by 10 matrix, and it can be calculated. So you could actually do this if you want to, but normally what you do is that you replace this one with the learning rate. And this learning rate, so now we have to be a little bit careful because I put the inverse here, so I should actually put the inverse, so that this equation which you see here becomes minus eta at iteration n multiplied with the gradient of the function you want to optimize. So you get this Newton's method by making a Taylor expansion of the function c, stopping at the order of the second derivative. That gives you Newton's method. And since the function we want to find the roots of is not the function c, but its gradient, that's why you have the gradient here and not the function value. The way you probably have seen it before is that you would see this as the first derivative. So you would typically see like this, inverse, multiplied with f of x, and x is calculated at an iteration n here. But since we are driving the gradient to 0, we are looking after the roots of the gradient, and that means that we get the second derivative instead of the first derivative here. And that's a matrix. That's a Jacobian, where you need all the partial derivatives. And that clearly is a complicated object. And that's why we normally replace that one with this parameter here, which is called the learning rate. And there we have different methods for doing that. The simplest way you would often start your calculations is just to keep it fixed. So you could set up an array of learning rates. Like this, you could have an array of eta values, which could span from, let's say, 10 to the minus 5, 10 to the minus 4, and it could go up to, let's say, 10 to the minus 1 here. That calculation, if you have many parameters to fit, that calculation is cheaper than you calculating the gradients, the derivative of the Hessian matrix. And that's why people simply run such calculations, and then you find an optimal set of values for eta, which gives the best reproduction of the data. And with that, you can start using other methods. So it's pretty common as a strategy to just set up an array of learning rates and run through with that with a plain gradient descent. Then, when you've done that, that is when you would typically then go back. So let's just look at that one before we take a small break here. So if we now go back and you look at these codes here, you will then see that now next you can do is to add momentum to the plain gradient descent, or you can update the learning rate. So these are the typical methods which are coded in here. And you can easily rerun this. And there are examples here on how you can use them. So you plug in, this is the learning rate, momentum 0.009. This is the way you would use the Adams scheduler. So these are just examples. And here I take a small data set and I'm just running through that one. And it gives you the kind of results of the weights after I've used the different schedulers here. So these are typical methods which you would then implement in your own code. If you're using TensorFlow or PyTorch, you simply have an option where you write Adam, RMS prop, AdaGrad, etc., etc. Then before we take a break, there are examples here of cost function. So this is actually the mean squared error, or what we normally use in ordinary least squares. And this is simply the target value minus the input value squared. So this is x is actually your output. And that gives you the standard mean squared error. This is the logistic regression case. This is a cross-entropy case. So these are different functions you can use then in the setup here. And then you can use autograd, automatic differentiation. If you want to use JAX, it sets up the derivative of these functions. And these are the quantities you want to optimize. And here you have examples on the derivative of these cost functions valued at a specific value A, which you're plugging in here, which is this array. So these are just examples of elements which you need to have in the code. Again, if you want to write your own code. And then there's a series of activation functions, and you will see here there's a minimum set. We have the sigmoid, there's the softmax if you're doing a classification problem with more than 2 cases beyond a binary situation. We have the leaky ReLO, the ReLO function, and here we are setting up the derivatives for some of these functions. But at the end, if you want to have some flexibility and use many functions, you would then just use automatic differentiation for these derivatives. But some of these, it's faster to hard code them sometimes than using automatic differentiation. And here are just examples of usage of the activation functions. And then after the break, we're just going to go through the neural network. And you will see that the structure of this one mimics very much what you will see if you use TensorFlow and PyTorch.